Is it ready?
Yes, it's ready.
Okay, so yeah, again, thank you for the invitation. So I'm going to explain what is this universal differential equation thing, and feel free to interrupt me anytime, okay? This will be simpler. So let's start with an old result that is quite famous if you're into those things. It's from Rubel in 81, so it goes like this. For any function f, continuous function over R, and for any epsilon, which is also a function, with the only condition that it is non-zero, there exists a particular solution y to this differential equation that approximates f within epsilon everywhere. So in particular, you could take epsilon to be a constant. That means for any continuous function, there exists at least one solution to this equation that's always epsilon close to the function you want to approximate. But you could take epsilon to be even a fast decreasing function, like exponential minus t, and it would still work. And what's very strange about this result is that this equation is explicit and particularly simple. And there's no reason why it should exist. And I think the first time you see this result, you can't believe it's actually true, because it's very surprising. So what I'm going to argue is that this result is in fact quite disappointing once you really understand it, but we can still do better. So
could you pause for a moment so that we can observe this surprising result?
So it's really just that this equation, it has many solutions, and those solutions, you could say, in some sense, they're dense in the continuous functions. That's another way you could almost phrase it. Except that this epsilon can still depend on t, so it's really strong. Is it?
And did he
clear?
Comment on if one? How did he get that explicit equation?
So I'm gonna try to explain how he got it, but I think that's like the core of the paper. The magic is that he managed to get something which is very simple. Because if you look at the paper, like midway through the paper, the equation is nothing like that. It's more like a full page of equation. But for some miracle reason, at the end, everything simplifies and you get this equation. And I cannot explain why it's the case. It just, maybe it was so clever he managed to find the right way of phrasing it to get a simple equation. And after this result, of course, there were many other results. Like this was simplified. You can see this uses order 4. You can actually go down to order 3. You cannot do it with order 2. And then you can do other things like maybe you take a different notion of solution and you get different results. You can do it over a compact set, but for stronger notions, there are many results of this kind.
And can you do this in the form y to the highest derivative is equal to a polynomial of...
Sorry?
Could you do it in the form y, say, fourth derivative is equal to
no. I mean, okay. I guess a consequence of my result is that you could, but it's not obvious at all. It's actually very, very important. It's very important here that, for example, this y fourth is multiplied by something that can be 0. It's actually absolutely crucial for the proof. In fact,
it's crucial.
It's crucial because it's going to let you create infinitely many solutions. Otherwise, you would have unicity, and then things like that's basically what I'm going to talk about. So it's very important that it's not of this form. But of course, it's not obvious when you see it like this. So have you absorbed the results? I'm going to explain how it works. Maybe it's going to make it less mysterious, hopefully. So in general, obviously, you could rephrase it like this. Okay, this is a particular polynomial algebraic differential equation. Okay, so this was the explicit one. This is the non-explicit one. And the question that Rubel asked in the paper is, can we have unicity of the solution by adding some initial conditions? That is, if I add something of the form y of 0 equals something, is the solution unique? It turns out for the equation he proposed, it's not the case. And in fact, we'll see why it's not the case. So already Rubel was aware of the defect of this equation, you could say. And to understand why, let's look at the proof. So it's a simplified proof, but it still fits on one slide, so you get the general idea. So it starts like this. Let's consider this nice bump function. So it's 0 everywhere, except in -1, 1, where it's this exponential of -1/1 minus t squared. Okay, why not? And you can do the math. It satisfies this particular differential equation. Okay, so far so good. There's really nothing special. And now what we're going to do is that we want to have a lot of bumps. We're going to want to build bumps. So what we want to do is take a bump and rescale it and shift it somewhere. So one way to do it is to say for any ABC in R, we want to consider this rescaled and shift bump. And now what kind of differential equation does it satisfy? Well, again, you can do the math. It's pretty boring, but at the end of the day, you can show that any such bump satisfies this equation. So what you do is that you plug the ABC and then you eliminate the ABC because you don't want the equation to depend on them. And you can do it, and it turns out that you have this equation.
How do you get rid of t?
That's part of the magic at the end. Getting rid of t is somewhere, if I remember correctly. I mean, really, there's no reason why this should work. I mean, I really have no idea how I came up with this. So, okay, we have bumps, but okay, a bump is not exactly dense in continuous functions. And this is where the crucial and magical step of the proof goes. It turns out that if you take this equation and you modify it a little bit, if you take two bumps and you sum them together, it's still a solution. So you can do things like 0, a bump, 0, another bump, and you can do it like everywhere. And the reason why it works is essentially because the way this equation is built, you can cancel the term that multiplies the highest order derivative. And at this point, that means you can have one solution and glue another solution, and they're unrelated. So it's crucial that at some point you can cancel something, and then you have freedom for the rest of the solution. So you can build the solution piecewise, and you can glue bumps like this. And once you have this, in fact, it's done, because now you can just integrate the bumps. And what happens when you integrate a bump is that you have a steep curve, but then in between the bumps, it's 0, so it's a constant function. So in fact, when you integrate those bumps, you have something which is like pseudo-piecewise linear. And obviously, since you can do that everywhere, infinitely often, this is going to be dense in C0. So that's how it works. And the magic is really this step where you modify the equation a little bit, and it turns out you can glue solutions together. So that's where I cannot really explain how I came up with it, but it works. But at a high level, it's really just that. Like you glue solutions, and I think now you kind of get the feeling why the solution is never going to be unique. It's because this gluing process, there's no way you can make unicity of the solution by adding conditions. Is that clear how it works? So yeah, that's the magic, but that's also the problem with this equation. So you never get unicity, and this is fundamental. It really relies on the fact that you can have one solution, then you cancel the highest order term, and then you can do something else. So there's no way you could say maybe we can fix the equation and add more conditions. This is not true. You could even add a condition at every integer that would still not help you. So fundamentally, this requires non-unicity to work. So you could say Rubel's statement that this equation is universal is kind of controversial, because what does it mean to be universal when you allow anything? Like if you think about the universal Turing machine, okay, that means you can simulate everything. But here it's just saying, okay, there's no rule, you can do whatever you want, then of course you're universal. But it's a very weak notion of universality in some sense. And of course he was aware of this problem, so he asked, like, can we do something where the solution is unique? And one way to recover unicity is to require that the solution is of this form, because if you have y prime equals p of y, then p is locally Lipschitz, so solution is always unique. So that's one way of recovering unicity. But of course, now we cannot do this trick that Rubel has done. So what I'm going to talk about is a positive answer to Rubel's question. Can we actually have unicity? The answer is yes. So there are two ways to phrase the results. One way is to phrase it the way Rubel hinted at, which is you say, indeed, there exists a fixed polynomial p. So this is a multivariate vector polynomial. Okay, the equation is going to be a system of these, and such that for any function f and any epsilon, just like before, now instead of choosing the solution, we choose only the initial condition. So this is a vector of real numbers. We plug it at time 0, and now the solution we know is unique, entirely defined by alpha, and now it satisfies exactly what we want. So notice that the difference is now, I'm only talking about y1, so the first coordinate of the equation, because now y is going to be a vector of functions.
But then does it depend on different choices of epsilon? A solution for a smaller one should also be a solution for a larger epsilon.
Yeah.
So why is it going to be unique?
Oh, it's unique in the sense that for every alpha there's a unique solution, but of course for every epsilon there are infinitely many choices of alpha that could do. So I'm just saying there exists one alpha that's, and once you pick that alpha, y is unique. So of course there's no reason why there should be a unique way to do it.
So, but like, is it true that you cannot approximate the whole y vector? Like, if I have f not a function but also a vector of functions?
Yes, I'm pretty sure you couldn't do it. If you really wanted to approximate all the components, that would be way too constrained. It's not a theorem, but my guess is you could find a continuous function such that it's very different from any like polynomial differential equation, like over all components. Like you could do crazy things, and then there's no way you can find a polynomial that matches this behavior. I mean, at least I wouldn't be surprised. So yeah, we only approximate on the first coordinate.
Okay.
But if you don't like this formulation with the system of ODEs and blah blah blah, there's another way to phrase it. So just some, I'm going to talk about it later. So some remarks. This is a system of ODEs. Side remark is y is necessarily analytic because the solution to a polynomial ODE is always analytic. Something which was not true in Rubel's equation. In Rubel's equation gives a C-infinite solution, but this gives analytic solution. And if you were hoping to have a concrete P, just give up right now. Okay, we need about 300 variables to do this.
Explain need, meaning it's necessary or it's sufficient? I don't understand.
That's what we need for our proof to work. Obviously, there could be a better way of doing it. I just don't know. But our proof requires about 300 variables to do it. And we don't even have an explicit expression for P because, as I'm going to explain, we don't build the equation explicitly. We build it in another way, and then we prove that we can rewrite it as a polynomial. Because you can imagine what a system of these with 300 variables could look like. This is absolutely nightmarish.
When you say y sub 1,
Yeah.
what do you mean by that?
First component of the solution. So it's
It's a vector differential equation. It's not make like a system. It's a system.
Okay.
For example, if I had two variables, I would have like something like that. And same for so f and g would be polynomials in my case, and I only prove that this particular variable approximates f, but I say nothing about the other variable.
But it doesn't have to equal f?
No, it's not.
Because it's going to work for any epsilon.
No, it's not equal. The y1 is never equal to f. It's just within epsilon of f.
For different epsilons, there might be different alpha.
For each epsilon, there exists a solution. So so there's a family of solution that converges, but
Yeah.
I mean, if f is not analytic, there's no way you can have equality anyway. So, and actually, even if f was analytic, you still couldn't do it because they're analytic functions that are not solution to ODEs.
Could you explain what P looks like? I mean, in terms of your first order equation y prime t equals P of yt.
You mean what it looks like?
Yeah, what does it mean?
P is this. It's just a shorthand for this.
It's a vector of polynomials.
So here P would be it's a vector of polynomials.
And
So that's P. So for example, you could have P of xy equals I don't know, x plus x squared
no,
y.
I got that. And then what is the first order equation say?
It's not
It's
first
not
order,
first order,
it's 300th order.
No, it's y prime.
Yeah,
No,
it's
it's vector.
it's first order, but it's a system, so you can easily express higher derivatives like
No, I
this.
understand that, but
It means that.
It's like the thing that you used to. It's nothing new.
Yeah, put a bar on top of one.
William, it's like in differential graph theory, but non-linear equation. It's the same form. Like this, or like 300th order.
For example, for linear equations, you have things like
no, I
that.
just don't understand why you write it that way.
Okay, that's his notation he's used
The
to.
connotation.
There are many ways.
Yeah,
For example,
now that notation I understand, right?
but now it's the same, but instead of having ax, which is linear, I
Yeah.
replace it by p of x, where p is a vector value polynomial function.
Aha, okay,
Uh,
all right.
it's a shorthand notation because if you really write it explicitly, it takes like the half of the slide every time. So
Okay, so, but right now, the way you write it, the y1 and y2 and y3 have no relation with
no,
each other.
no. I mean they have no relation to f, but of course the equation uses all of them. So you need those extra variables.
All right.
You need them to. They're auxiliary variables. Okay, is that clear? And just
What would you say? What kind of impact do you think it would make on modeling?
well, a consequence of this results, in some sense, is that if you have a system and you're hoping to find some like an ODE that would be the law of the system, then in theory you should give up right now. There's a law that will match almost any observation you can make. This is what this ODE says. Of course, this is a really bad answer. Okay, this ODE does not exist in nature. That's pretty clear. In fact, any noise you could add to this would completely break the equation. Okay, this equation really relies on the fact that it's exact. Any noise would make it crash in some sense.
And you only know how to do it for 300 order. So if your laws are of lower order,
Yeah.
you're not sure if it's bad. You don't know, but
Yes, exactly.
Okay.
So you could take that as a result that okay, trying to guess the law of a system is hopeless if your system is too big. But of course, this is not a good answer, I think. So you should.
What are the degrees of the components of P?
They're pretty high, but if you're willing to have more variables, you can always go down to p of degree 2.
If you fix 300,
So I don't know, if I fix 300, I don't remember what the degree of p is. It is pretty high, I'm pretty sure. Like, I don't know, at least 10 or more.
So can I read your main result as adding the fact, as the hypothesis that for all d greater or equal to 300?
Yes, I mean, you,
approximately. So here,
No, I
I-
understand, but you see, the d here was not described.
no, they exist, yeah, of course. So when I said there exists a fixed vector polynomial, in fact, there exists a d such that.
there's a missing quantifier. There exists a D.
There exists a d such
There
that.
exists a d.
Yeah.
Okay.
Yes. Because of course, the polynomial, like to describe the polynomial, you already need to know the degree, but so I didn't put the quantifier for d.
But the only requirement for there exists a d is that the initial condition involve d numbers.
Yes, the initial condition will.
In other words, you require y to be a vector of dimension d.
Yes.
Okay.
Yeah, of course. Yeah, I didn't write. It's for like just to make it more concise, because obviously the fact that alpha is of dimension d implies that y has to be of dimension d.
Right, of course.
If you go to look at the paper, there will be all the quantifiers and all, but then the theorem is like twice larger than this. So
Okay.
I'm sorry.
No, that's okay.
It was slightly more precise for the slides. And actually, we proved something slightly stronger. We proved that this alpha it's not like an alpha that comes out of nowhere. You can actually compute it from f and epsilon.
So that means you can compute D first?
So D is always fixed. D is always about
Is
300.
D given or not?
D is constant, fixed forever. It's like somewhere around 300. It doesn't depend on f and epsilon. The equation is fixed one for all.
So this is the first point. It starts with the quantifier D. There exists a D such that blah blah blah. There exists a D such that, and so he says it's approximately like 300, maybe 305.
No, the point is, if there exists a D, then can you compute D?
Yeah.
He knows it exactly.
Oh, because then you can compute alpha, you say that.
He just knows it.
All right.
Just knows it.
I know what P is. I mean, if you want to know what P is, go and look at the proof, unfold all the proofs, and find P. But
I'm just saying that when you say alpha is computable, does that include computing D?
but D is fixed. It's
He's given.
D.
Is D given or not?
Yeah, of course. D.
But then somebody says there exists a D.
Yeah, because
Then how is it given?
the theorem just stated like this. This theorem doesn't give you the explicit P. Okay, it just says there exists a P.
No,
And there
I'm
exists a
talking
D.
about D. not
Yeah, but P. I mean, we need D to. P
It's okay,
is.
so I think he answered your question.
Everything is fixed. D, P, all of this is fixed forever. It's just that in the theorem, I didn't write it
Oh.
because it would take 100 pages to write the explicit P.
It would take 100 minutes to go back and forth to address that.
And we'll get down to
But
80
you
minutes.
see, if alpha is computable, then D has to be computable.
But D is.
No, if you compute alpha, then you know the dimension of alpha.
That's okay.
And that's D.
Yeah, that's okay. So he knows the D. Okay.
I know the D.
Okay, so he,
It's
Okay.
it's about
If
300.
you know D, then it's a given thing, not an existing thing. If the theorem
can
says
phrase
there
it-
exists a D,
phrased it like that.
you can still phrase it like
no,
that.
if you said there exists a D, then you don't know what it is.
Okay, thanks. So he got your comment, so he can improve
Alright.
later with the slides. He got
No,
your
I don't understand what the main theorem says.
Okay, do you understand it now?
No.
No.
Okay, like well, so okay. Let's rewrite the theorem. Okay, now my theorem will be there exists a P and blah 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 blah, and everywhere we substitute D by like say 300. Okay. So everywhere you see D in this theorem, just replace it mentally by 300.
Okay.
Okay.
Is
But
this
now-
clear to you?
So if you can replace D by 300, then D is computable.
Yeah, D is fixed.
It's
But
fixed, but yeah, you compute it and it's fixed.
Yes,
fine.
yes. And by the way, can you still bring some hope to those who do modeling? So that do you expect some theorems that for much smaller D that's impossible, and for like if you have D say 50 and polynomial degree 2, can you say it's
it's hard to say. At least with this approach, I don't think you could have a really small D, like because the way we build things, we construct things on top of each other to make it simpler to understand. But at the end, when you rewrite, you always explode the number of variables. Maybe there's a really clever way of doing it, but you would need to be really, really clever, I think.
And your approach is for showing results in such a way, and is would your approach be able to give a positive result as well? Like you prove you're thinking to construct such special examples. Do you think that you could also that your approach prove that they don't exist, or it's
No.
different proof?
No, it would be completely different.
Mm-hmm.
Now, the way I approach things is that I build things. I show they exist. But that really doesn't help proving things don't exist. And actually, it's quite hard to show that things don't exist in this setting. It's really hard to show, even for simple examples at the end, I can give you a concrete question I don't know the answer to, and it's of the form show that it does not exist. So, yeah, I think it's quite hard to show things don't exist.
Thank you.
And so, just to say, I don't want to say too much about it, this alpha is computable from f and epsilon. This statement can be made precise if you know computable analysis, but otherwise just imagine that if you were given f and epsilon, then okay, you can there's an explicit expression for alpha in terms of f and epsilon. Okay, I don't want to say much more. And if you don't like ODEs, and you don't like this system of equations, you can also rephrase it as a differential algebraic equation. It's going to look exactly like Rebel's statement. There exists a fixed k, so k is going to be a bit more than 300, I think, and a non-trivial polynomial p such that for every f and epsilon, there exists a solution to the DAE. This time we add conditions, but to enforce unicity, now we don't look at all the solutions, we only look at the analytic solution. And by construction, there's a unique one. Okay, so here I'm not even sure if you had a DAE in general. It's not even clear there's a unique analytic solution, maybe, but at least this equation has, and it satisfies what you want. And in this case, y is not a vector anymore; it's really a function.
By the way, is there some kind of version of this that would make sense for recurrence relations?
So you mean like you approximate at integer times? Like you try.
Can it make sense and say something about discrete models?
Yes, I think it's plausible. Yes. But yeah.
So you think that your approach would exhibit a very similar pathology with discrete models?
I think it's possible, but maybe you would need something which is a bit more than polynomial, though. I'm not entirely sure. I would have to think about it. But you could do similar things for discrete, but it would be a bit different. So I'm not sure you can just reuse the proof like this. That would be a different proof. But using similar ideas, you can do things of this form, yes. So just some motivation, and then I'm going to switch to how it works, but at least some motivation where this comes from, because I'm doing computer science and this is a pure math result, so you might wonder why I look at this. The reason is those polynomial ODEs, which we don't know much, like how they behave, they can be extremely complicated. In fact, they correspond to some models of computation in computer science that are called analog. That means they're not using transistors, they're not discrete, they're not like Turing machines. And it turns out, if you go back 100 years, in the British Navy, they used things that they really called computers, and they were those complicated mechanical machines. And when they had to solve differential equations 100 years ago, they didn't have Maple, they didn't have Mathematica, but they had the differential analyzers. It was a tracing machine where they would have belts and gears, and things rotate, and they solve differential equations. And it really works. It's pretty slow, but it works. And the funny thing is that we've completely forgotten about this. But from the point of view of computer science, it's interesting to understand what you can compute with those things. And so in particular,
is this like an analog computer, or?
Yeah, it's an analog computer in the true sense of analog. So you could also do.
As analog computers used before digital.
Yep. Yeah, exactly. Because that was like before the invention of the transistor. So everything was mechanical. You could do it with electricity as well.
Can you just use it with RCL circuits?
Sorry?
Can you just use RCL circuits for analog computers?
Yeah, you could use electricity instead of mechanical.
Mechanics, right?
Yeah, you could use. Yeah, it's the same.
Okay.
Yeah.
Many of these were electromechanical.
Yeah, so at first they were only mechanical, then they were electromechanical, where the electricity were just to help things turn, because you need a lot of strength, like you need a lot of torque. And then eventually they become entirely electrical, like with analog circuits, and then they were just discarded. So yeah, there was a whole history about this. And it turns out that in fact those machines, you can prove they're equivalent to Turing machines in some sense. And you can even characterize complexity classes with these things. So surprisingly, analog computers, from theoretical point of view, are no different than your regular and favorite computer, which is quite interesting, but it's not the subject of the talk. But the takeaway is that polynomial ODEs, in some sense, you can see them as a programming language. That's how we approach things to prove this universality result. And this is just one example of how you can like transform like a circuit to a differential equation. So if you wanted to implement a differential equation on a computer, you could like take this, draw boxes, and then implement them physically, like with electricity. Okay, so I'll try to explain how this proof works at a very, very high level. But before that, I need to explain a little bit more what I know about polynomial Ds and how you can build stuff with them. Because doing things by hand is just not an option. I mean, I guess you imagine that you cannot build a system with 300 variables by hand. And so it's very simple when you start. I'm just going to give a name to solution to ODEs where I only look at the first component, okay, which is what I've been doing with those systems. I only look at the first component. So I'm going to say function is generable if there exists a particular system of ODEs such that the first component is f. Okay? So in other words, it's just any function that you can obtain with a differential equation by adding more variables. Okay? Is that clear? So for example, there will be more example, but you could say for the sine prime is cos prime is minus sine. This is a linear system, so particularly it's polynomial. Thus, sine is generable. Okay, that's just trivial example of what does it mean to be generable. Here are the types if you really like formal things. Unicity in existence of such a y is of course given by Cauchy-Lipschitz theorem because P is a polynomial. So there's no problem with this. And now one thing which I'm going to do is try to see what is in this class. What can we do with differential equations like this? So obviously you can do polynomials, okay? The x is generable because x satisfies x prime equals 1, okay? More generally, you can do squaring, okay? Not very surprising. You can do any polynomial. You can do exponential because you can do all linear differential equations, okay? I've told you about sine and cosine, okay? So here you need two variables. Don't look at the explicit equations, they're not very interesting in general. Another function which can be very useful is the hyperbolic tangent. It's very important because it converges to some value at the infinity, which is quite useful. You can do rational functions in general. The idea is just that you differentiate and then this is usually expressible as the original function. And then you just need to write polynomials. So we've seen that we can do polynomials. So we can do any rational function like this.
Is the set of generable functions a field?
So we'll see,
Okay.
actually. So now, those were concrete examples. But now what's interesting is that we can take solution and build more things from them. So in particular, if I have two functions, g and h, and I know they're generable, then it's not hard to see that the sum and difference is also generable. For the obvious reasons that the sum and difference commute with the differential. Okay. You can do the product for pretty much the same reason. Okay. So again, not very surprising. You can do the inverse, provided that of course the function doesn't cancel. And again, this is just a little game of rewriting. So actually, it's a field in the sense that you can always divide if that makes sense. But actually, you can do much more, which is where it becomes interesting. You can integrate functions, because you just have to write my derivative as what I want, and then immediately you're the integral of something. You can also differentiate. This is a bit more technical, but if you have a function, then its derivative is almost constructed by the system, because it's a differential equation. So it's more like a differential field, in fact. But you can also compose functions, so things start getting interesting. For example, if you ask me, is sine of hyperbolic tangent of x generable? I'm like, I have no idea, but it's the composition of two things that I know are generable, so yeah, its answer is yes. And again, it's just a little game of like doing the math and writing. There's a little technicality on the coefficients you have to allow. in those differential equations. So if you're willing to have any coefficient, any real coefficient, then there's no problem. But if you want to restrict yourself to something less, then you cannot go down to rational numbers if you want stability by composition. I'm not going to talk about this too much. And now this is where things get really interesting. Suppose I take the solution to this differential equation, which is not polynomial. Okay? F prime equals hyperbolic tangent of f. You might ask me why I want to do this, but I assure you it's very useful actually. Is this generable? Well, you can write it, and it turns out, yes, with a few variables, it's generable. But then once you do it, you quickly realize that to prove this is generable, you only need to know that hyperbolic tangent is in fact generable. So it turns out this is a special case of a much more general theorem, which is that if f prime is equals to g of f, and g itself is generable, so previously that was my hyperbolic tangent, but now replace hyperbolic tangent with any generable f, then the solution is still generable. And in fact, that means that we're not going to look at polynomial differential equations. We're going to look at generable differential equations. So suddenly the class of things we can do is like just exploded. We can do much more things. What does it mean? It means that we have this nice theory of like those generable functions, which so far are always total and univariate. They're always analytic. They contain plenty of things. They're stable under all those things. So it's a field, but it's more. And that means that polynomial Ds are a very large class. Okay. Now, of course, this is nice, but this is not quite enough if you want to do the proof, because those are always total functions, but we will want to use non-total functions. For example, if you want to have the tangent, you may want to use tangent, but tangent has singularities. So you want to work around this. And they're always univariate. And univariate functions are nice, but to build things, we're going to want to use more than one variable. And I'm going to go very quickly through this, but you can take this notion of generable and extend it to multivariate and open connected domains. And now we need to switch to partial differential equations of a very special kind. So here, y is going to be a vector, and we're going to express the partial derivatives in all directions as a polynomial. So it's going to be an over-constrained partial differential equation. So unicity will always be given, but existence, however, is non-trivial. So the way we're going to do things is that we always ensure that when you write something, it exists. So we only prove existence of object. That's why my approach doesn't allow to prove non-existence of objects. I just prove things exist and nothing else. But I don't want to go into the details. Things get horrible. Like just very simple equations become horrible, but you can do it. But for example, you can give a meaning to this function is generable, and this function has two arguments. And you can give a meaning to this function is generable, although for x equals 0, it doesn't make sense. Okay, that's all that you need to know, basically. And so what I've said before for total univariate function, well, it just applies now to everything. So I can do multivariate generable functions over connected domain. You need connected because since we're going to write differential equations, we only have one initial condition. So to have unicity, we need to restrict ourselves to something which is connected. Otherwise, it doesn't make sense. We will not have unicity. And the nice thing about this is that, sure, at some point, we're going to require partial differential equations. But at the end, if the function we write is univariate, it's a polynomial differential equation. So in the middle of the proof, we're really writing partial differential equations everywhere. And at the end of the proof, we end up with a single variable, and we know it satisfies a polynomial differential equation, ordinary differential equation. So that's very useful for the proof, but it doesn't appear in the results. Is that clear? So now we're going to use this, this thing to build functions. Just exercise, I mentioned it before. Is it the case that all analytic functions are generable? So I've told you no, but do you have a guess at which functions may not be?
Gamma function?
No,
So gamma and zeta function do not satisfy
any differential.
algebraic differential equations. So why is this useful? As I mentioned, writing polynomial is hard. So let me just give you one example of things that, if you wanted to do it without what I've just described, would be maybe not impossible, but really hard. In the paper, you would find something like this. There exists a general function round that basically is an almost rounding function. So it's like around the integers, it's very, very good, and around it's just continuous. So it looks like this.
Could you break the chalk into pieces?
Yeah. Maybe I'm gonna erase this. So you can find an ODE that does something like this. Here it's almost 0. Then here it goes up to 1. So here there's some behavior, we don't say what it is. Then it's almost 1. And it goes there, it's almost 2, almost 3, and so on. So it's an almost rounding function, but of course it needs to be analytic, so it's never quite 1 or never quite 2. And actually what we're proving is something even stronger. Now we're saying, in fact, you can add more argument to this function, so it's going to be a partial differential equation, and you can control how good you are. So this mu tells you how precise you are here. And this lambda tells you what is the size of this band where you know you're not going to be good. You have to be continuous and analytic. So using those tricks of building function, composing them, and all, you can build functions like this round function, which if you were trying to explicitly write a differential equation that satisfies this, like, I challenge you to do it. I think it's almost impossible to do it by hand. And actually, the expression for this is like it's like half a page, so it's really hard.
How did you do it?
It's some kind of nasty trick using sine, cosine, tangents. I cannot describe it in just 5 minutes. It's quite technical, actually. It's quite technical already, knowing all what I've described before. So this is the kind of things we can hope for with this theory. So let me just remind you the result, and now we can go to the high level of the proof. Not going to give like super technical details, but those would be pictures. So what's the general idea? The general idea will be the following. So this is going to be very vague, and then I'm going to be more precise. We're going to build a bunch of ODEs. So the first one will be given alpha. We're going to build an ODE that produces a solution that is almost 0 and almost 1 all the time. And this stream of 0, 1 is going to be the digits of alpha. Okay, written in base 2. Okay, so as we'll see, this is possible to do. Already, you see like how you do this in practice. It's not so easy. And then what we're going to do is that we basically going to integrate this stream. So this is something which is well known in signal processing. We're going to convert this stream of bits to an analog signal. So if you have your computer and you're listening to music, your music is stored as in some digital form, a stream of 0 and 1s, but you're listening to something which is analog. The computer is converting the stream of bits to some analog. This is called digital to analog converter. This is basically what we're doing. We're converting this stream to some analog thing. So you could think about Fourier, for example. This is not how we do it, but this is one way you could do it, maybe. But there will be one restriction, though, which is exactly the restriction you have on the computer. We can always only do it for bounded functions that are Lipschitz and for a fixed frequency. The computer plays music at a certain frequency. You cannot reproduce the entire spectrum. This is, of course, you cannot hope to reproduce any sound. So you have to limit yourself.
Could you again clarify what the second arrow is doing on top?
This?
No.
Left. Horizontal.
Horizontal. Second horizontal arrow.
This?
Yes.
Yeah.
Yes.
Oh, it's just, this is the solution that it plots. Sorry, it's just like... This is if you look at what this ODE produces. It's just and this is very vague so far.
So, but just so you mean this is not of alpha, but of solution for alpha? Because like you start with alpha, and after 2 steps you arrive at digits of alpha. Why do you need ODE in between?
So it's going to be an ODE where you plug alpha basically, and it produces this this solution that produces the stream of bits.
So it's some tool to do that.
Sorry.
Or how is alpha given?
Alpha is going to be there exists some alpha. The way to choose alpha will be critical, but I don't want to explain it right now. So for now, let's just assume I plug alpha and things happen. Okay. Because for now you don't know how to choose alpha because you don't know what I'm going to do with this function. So for now, what I'm just saying is that if you plug alpha, you can find an ODE that produces a stream of bits, okay? And then you do something magical, you integrate it, and now you have this signal. And now obviously this signal depends on alpha.
In what sense does an ODE produce a stream?
As well, if you look at one of the components and you plot it, this is what you see. For any alpha, there's a plot that looks like this. Okay, this is.
Okay, so you go from ODE to actually that plot.
So there's the ODE, which is the complicated object, and if I look at one component, this is what I see. This is you could say this thing is generable.
You see digits, or you see that plot?
If
The plot.
after you see the plot here, I've printed the digits just to help you see what this plot is supposed to be. Of course, it doesn't print 0 and 1.
Right,
what
so
you see is the red curve, but this red curve corresponds to the digits of alpha.
Okay.
We're going to build strange things, okay? And the thing is, the things we build, they have some meaning. We build them to do something, but of course, like that's the intuition behind the curve. What the curve actually is very something quite complicated, okay? So from alpha, we build this curve which is almost digital. Then we integrate it, we have this curve, so we can produce things which are Lipschitz and bounded, basically. I can provide very good approximation to Lipschitz and bounded function. And then, from this, we need to take this thing, and somehow we need now to be able to approximate any function which is not necessarily Lipschitz and not necessarily bounded. So here there's going to be a step which is magical. We're going to go from Lipschitz bounded to anything with an ODE. And that's actually one of the crucial steps of the proof. We're gonna need to be able to build some arbitrarily growing ODEs. So let me just explain in a little bit more detail how it works. Hopefully it's going to convince you, but maybe not. So if you want an explicit expression, this is what it looks like, but don't look at it too much. So first we have this function. So we show it's generable, and if you plug alpha, it turns out this is going to produce things like that. Like this is going to print the digits of alpha, basically. It's going to alternate between almost 1, almost 0, in a way that depends on the digits of alpha. Okay? And then what we do is that we're going to build another function which, given a bunch of dyadic numbers, d0, d1, d2, is going to ensure that whenever I see a 1 like at the top curve, then the value of this function is going to be this d0. Then it's going to do something crazy. We don't care about what it does. And then when the other one values its value 1, there's going to be d1. So here, alpha, d0, d1, d2, all of these numbers are fixed. So if I fix them, I'm claiming I can find solution to ODEs that are like this. So the first function is like a clock. Every now and then it's saying 1. And whenever it's 1, the bottom curve has a value which interests me. So just to give you some intuition, what we're going to do is that the bottom curve is going to be a crazy curve that do a lot of things, and it does so many things that eventually is going to take a value that we want. Okay? And so whenever it has this value, the top curve is going to say 1. Yes, I want this value. So the bottom curve, its job is just to produce many different values that we want. So that's why it's doing all those crazy things. And we're willing to wait as long as it takes to get those values. We're in no hurry, so it doesn't matter if it takes a really long time. And then what we do is that whenever we see this one, we take the value that was given by the bottom curve and we copy it to another component of the equation. And now we hold this value until the next signal comes in. So the green curve is another component of the ODE. The only thing it does is that it stays constant, and whenever there's a 1 on the top curve, it copies the value that's on the bottom curve. So the bottom curve now, you see the signal is 1, so it just copy the new value. Then it stays constant, and then there's a 1 top curve, so it's another signal, up, copy the value. And again and again and again. And now if you erase the red curves, what you see is this, which is an almost piecewise constant function. So that's at the high level, that's how it works. We have two curves. We have one curve that tells us whenever things are interesting, and the bottom curve is just there to produce many, many values. And we just copy them whenever we see fit. Okay? So this, at the high level, this is how it works. And now you can see that we need Lipschitz functions because there's no way we can produce arbitrary values with the bottom curve very quickly. Because it turns out when we copy value, we need a small time to copy, so we need to make sure this value here is constant for at least a small amount of time. It cannot be arbitrarily small. So this is why this curve it has some kind of spikes, but they're always constant for a little bit. So whenever we produce values, we have to hold them for a short while. So we cannot produce too many values too quickly. So that's why we need Lipschitz. And on top of that, we need bounded because we're always going to be between -1 and 1. Okay, so believe me, this is the very technical part of the paper. We can do almost piecewise constant function bounded by 1, and which are Lipschitz. So we're super slow changing frequency. And now from this, we're going to build any function. So the intuition to go from this to everything is not particularly complicated. If you have a function and it's changing too fast, what can you do? Well, you just take that function and you compose it with a slow function. And now suddenly it becomes Lipschitz even. And if it's too big, for example, exponential, well, you just divide it by something which grows really fast. And now it becomes bounded. But the problem is if you have exponential, you need to build something that grows faster than exponential. But can you always build something that grows faster than a given continuous function with polynomial ODE? So that's a non-trivial question. How fast, can you build solutions that grow really, really fast? So I've mentioned exponential. Obviously, you can build exponential. Exponential is a linear differential equation. You can do 2 exponentials by having another variable. And in fact, if you have n variables, you can easily build a tower of n exponentials. That's just an exercise. So let's call this function en. So en is the tower of n exponential. Now, my question is, can you do any better with n variables? The answer is not trivial, because Borel, more than 100 years ago, he conjectured that no. He said, I don't think that with n variables you can do better than this. Okay, maybe you can put some polynomial here, maybe you can have some constant a. Okay, I give you that, but apart from this, I don't think you can do any better. If that were true, then my result couldn't hold. Because I couldn't do functions that grow faster than this. So it turns out he was wrong. And this was noticed already a long time ago. There's a very simple function that grows faster than this tower of exponential. If you're willing to change a little bit the definition of grows, you take 1/2 minus cos t minus cos of alpha t, and you take alpha to be irrational. So if alpha is irrational, this is always defined except for alpha equals 0. Because you cannot have t and alpha t that are both integer multiple of pi simultaneously. Okay? If it doesn't seem obvious to you, just think about it for a little while. But, however, alpha t and t can be arbitrarily close simultaneously to multiples of pi. So, so if you try to write the equation, I want t to be an integer multiple of pi. So I want to cancel the first cos t. And then I want alpha t to also be an integer multiple of pi. Okay? So that's what it would take to cancel this denominator. Then you can see the only solution is t equals 0. Okay, this is not very hard to see because there's no way you can write alpha as basically n over m. However, and this is basically Diophantine equations, you can find infinitely many t's for which this equation is almost true. It's almost true. And thus, what does that mean? It means that the cos t and cos alpha t will be arbitrarily close to 0. This is you can see it by density if you want. So there will be spikes. Spikes where the denominator almost cancels, but not quite. And those spikes, you can show that if you choose alpha really well, they can be really high, much higher than any Taylor exponential. And this function, you can write it with just like 5 variables of the system of a D. So it grows fast, but it turns out this is not good enough for us because we want something that grows even faster than this. We want spikes, but in fact we want them like really close to each other. This function has spikes, but you don't really control when those spikes are. They can be really far apart. In fact, they're getting further and further apart. So we need something better, and the trick in the paper is to build something that is like this, but even worse. It's like a nightmare function that spikes all the time, even higher and higher and higher. So what we have is something like this. You can find a polynomial p such that for any continuous function, so p is fixed forever, that for any continuous function f that you give me, I can find an initial condition such that the solution is always bigger than f, for any f. So for any f, there's an alpha. And that solves the problem. Now, if you give me an f that you want to approximate, then with this, I'm going to build a fast-growing function, and I'm going to divide f by this function, and now it's going to be bounded. And same thing for Lipschitz. You just look at the Lipschitz constant, local Lipschitz constant, then you take a function that grows faster, and then you compose by the inverse, and now it's going to be a slow function. And by this, you go back to the previous case, using this horrible function. However, there's just something which is puzzling, is that for this to work, we really need alpha to be transcendental. So alpha is going to be a really horrible number. And in fact, Borel's conjecture still holds, whether for rational or algebraic coefficients, like this Taylor exponential is really the best you can do. So everything I've told you so far, like those two examples, you cannot make them work with rational coefficients. So maybe a solution to your modeling question of before is require rational numbers, and maybe there's no universal equation with rational numbers. Maybe. And finally, I'm going to finish on this. There's one more thing we need to do with differential equation, and hopefully this is going to convince you that those ODEs is really like programming. Assume f is generable. So, I don't know, you could think x maps to 2x. Can we iterate f with an ODE? That is, can we find a generable y such that y at time n, when n is an integer, is the nth iterate of f? So graphically, this would look like this. want to build an ODE such that at time 0 it has value, I don't know, x, and at time 1 it's going to have value f of x, and in between it can do whatever it wants. At time 2 it will have value f of x, and so on
as well.
and so on. So at time n, I want it to have value nth iterate of f on x. So we know generable functions, they're stable by composition, but not by iteration. A priori, there's no reason why it should be the case. But it turns out, if f is not too bad, we can actually do it. And this is very simple. You just take two variables, the blue and red, and during half of the time, the blue variable is going to be constant equal to x. And during that time, the red variable is going to try to converge to f of x, f of the other variable. Okay? Converging to a value as an ODE is not very hard. You just say, my derivative is what I want to achieve minus what I am. Okay? And then you converge really fast, exponentially fast to what you want. And then during the other half of the time, the red variable, which is now f of x, stays constant, and x keeps up. It says, now I want to be back to the red value, because we need to be equal. And now you do this over and over again. During half of the time, the red is going to compute f of the blue, and then blue keeps up with the red. And that way, you can see that they're constantly computing f of the other, and thus you're iterating a function. And for this to work, you just need f to be nice, because you introduce error over time. So you need to make sure those errors don't accumulate too fast. And of course, this behavior of you switching between two behaviors is not polynomial, but you can implement it as a polynomial using all those tricks about the hyperbolic tangent and rounding functions and stuff. So you can iterate functions in this model, which is also how you achieve things. Okay, so to conclude, we've solved Rubel's problem, so we have a positive answer to his question. There exists a universal differential equation, which is quite surprising, at least. I didn't believe it could be true initially. I couldn't believe Rubel's result was true initially, but now I know why. And just a remark at the end, so I've said it before, alpha is computable from f and epsilon, but I didn't say that f and epsilon had to be computable. So it means that if you know f and epsilon are computable, then this alpha is computable. But if f and epsilon are not computable, then there exists an alpha that works, but this particular alpha you cannot compute it, which is very strange. So you know it's universal, but sometimes you cannot find concretely the alpha you need. But in all the cases, alpha is a horrible transcendental number, and it's not clear if that would work if you only had rational numbers. I think that's the open problem that's left here. Thank you.
Questions?
But like, if alpha is not transcendental, that wouldn't it like mean that there is not enough information it carries? So is there any like information theoretical explanation that alpha has to be transcendental?
That's a good question, actually. Yeah, maybe you could prove it like this. At least the conjecture on the growth is still wide open. Yes, maybe for this kind of result, like indeed, if alpha was rational, you wouldn't have enough choice.
And about the growth conjecture, what is this like common belief? What do people think about it?
I don't really know. I think they think it might be true, but
Might be true.
it might be true, but you know, like until you see this example with the two costs, okay, you might really think it's true. Like you try hard, you try to find examples, you're like, I can't see how you could do it. Then you see this example and you see, oh, it's obvious that it cannot work. But then it's the same situation again. Like you try, it doesn't work. Maybe it is an obvious example, or maybe it is not. So it's
Okay.
This is actually very reminiscent to me of small divisor problems in mechanics. I don't know if you've ever studied that. But it was an old problem about solving difference equations, and you write out a Fourier series for the thing. Your denominators are e to the I alpha minus 1. So if the alpha is rational, you have no solution. But if it's irrational, then you have a chance. And Siegel actually solved one of the major problems about that by putting badly approximable conditions on alpha. And that evolved into what's now called CAM theory for Kolmogorov, Arnold, and Moser. And they're implicit function theorems for solving such problems. It's a big industry.
Okay, that sounds interesting.
Yeah, you might look up just KAM theory.
KM, okay.
And it's very, that example just reminded me of that. Very close.
Yeah, I think it's related to how good you can approximate numbers, because already in this example here, if you take alpha to be not irrational, irrational but algebraic, for example.
Yeah.
Algebraic of fixed degree, then you can show the growth is not arbitrary, it's bounded by a function of the degree. So you really need alpha to be transcendental to achieve anything,
Yeah.
but any irrational number will of course make sure it doesn't explode. So
Yeah, it really comes from approximating
yeah.
rational.
By the way, so when one is doing modeling, say you have a system with parameters, is it safe to assume that the values of all the parameters are just rational numbers?
I don't know. Is nature rational? I don't know. I mean, pi seems to be a very common number. It's transcendental. But obviously this alpha is not pi, okay? It's something much more horrible. So it's I don't know.
But is it fair to say that there are plenty of models that don't involve irrational numbers?
I guess so. Yeah, I guess. But it's always this question about the difference between the model and the reality. Right? It's what is the meaning? Okay, there's a model which is rational. There's a model which is irrational. For all intents and purposes, you cannot see the difference. But you don't even know what's the relationship between this model and real life. So I don't know. It's a philosophical question. Okay.
In the case where you have just one variable and the other ones are the derivatives, the alpha being the initial conditions, what is the geometric significance? So you look at a point with 0, and you look at the way the curve actually grows, like the Taylor series, and assigning these alpha there forces the approximation to be unique to F, right? What is the geometric meaning of that?
You could just say there are infinitely many. If you just look at the equation without initial condition, there are infinitely many solutions, and this alpha is just I pick one of them.
Right.
You just this solution exists in Rn, where n is big, it's like 300. But now you say I want the only solution that goes through that point at time 0, and now you've selected one solution. That's just the meaning of this. That's one way you could do it. You could see it.
No, but the point was to choose the alpha to force it to, not only be the solution of the equation, but also to actually approximate F.
Yeah, of course. But that's, this alpha we should exist, but that doesn't have really a meaning except selecting the right solution. I cannot tell you anything special about this alpha.
I'm trying to understand. So, the actual meaning of approximating F with a solution, because F doesn't satisfy the equation, right?
Yeah.
So why would of course, knowing enough of the so you're saying knowing enough of the Taylor series of a solution tells you about F? Of course, the alphas depend on F and epsilon, right?
Yes.
Yeah.
No, it's
No?
yes, it depends, but I don't think you should see you shouldn't interpret this alpha as some kind of Taylor series of f. That's
No,
really
no,
not
not of
what it
f,
is.
of the solution, of f, of y.
Yeah, not really, because
Well, it's
The-
the
the
beginning,
what-
it's the beginning.
was the beginning, yes, but I mean because you can express the derivative of y as a polynomial of y. Once you fix the value of y, then all the derivatives are immediately fixed by the equation. So
Yes.
it's not really a Taylor series. It's like once you fix the value, everything is
Of course.
defined. So.
And how does the higher order initial conditions of y get influenced by f and epsilon?
It's just it's a vector. Why is a vector?
I mean,
No. I'm thinking about y as a function, and then the other part is the derivative.
well, you have.
I mean, the nth order.
So you want to control this?
If f was a single variable, okay, not a vector, to make things simpler. If you have y prime equals f of y, then obviously you have y second equals
Right.
y prime
Right.
f of y, so that's going to be f of y, f prime of y, okay, so and so on and so on.
But
So,
f need not even be differentiable or anything, right?
well, f here, I mean, okay, f actually is here is p.
Oh, okay.
So p, it's a polynomial, so it's infinitely
Differentiable.
differentiable. So
Yeah,
all the derivatives are fixed.
Exactly. So the initial condition only, if you actually know, let's say p is order k, right?
Okay, degree.
Then, yeah, or no. Oh, okay, you call it degree, but
Okay.
no, it's not degree. The number of variables in p
Okay. So
is the order, and so after that order, the initial condition will be determined automatically by the previous one, right? By the first k ones, right, from your equation.
yeah, I mean it's.
So if p is your differential equation of the order 4, let's say,
Mhm.
then when the first 4 initial condition of y is known, then the rest of the initial condition would have to be
Yes.
fixed because y is fixed already. How would increasing d to fit f and epsilon be affected by the later alphas?
Because the behavior you can achieve with a small number of variables is very constrained. They're constrained. If you have a differential equation of
No, but
order
you- but-
two,
but it- no, but it-
you cannot achieve some things. There are things you just cannot do with differential equations of degree 2, but you can do them with equations of maybe
When
order
you say
3.
degree, you mean
Order.
order?
Yeah.
No, but the point is that you. Oh, I see. Okay, so. Okay, so no, so P is not really the Rubel equation of order 4, but of a much higher order. You're saying, in your case.
Yeah, in my case, there are 300 variables, but
That means order 300.
yeah, order 300. But
I see. Okay.
I don't have any concrete example of things I could do with 300 and not 299. It's just, I don't know why I need 300. That's how I built it, but there are theorems that show with order 2 or 3 you cannot do it. Because it's just too small. But then starting from order 4 or 5, it's too complicated already, so we don't really know.
Okay, more questions?
So the uniqueness problem that Rubel asked, if it is specific to the example P that he gave of order 4, is still not answered.
Well, I mean, his equation cannot be fixed. Like, there's no way of adding initial conditions to his solution to make it unique, and there's no. It's just the way it is built. It just cannot work. So his question is really: is there another equation for which it will work?
Okay.
That's what we saw in the proof. The fact that we glue solutions, like glue bumps together, we can do it infinitely often, just means that for any finite number of conditions you add, it's still not enough.
let me just say that the way you construct it doesn't work. It didn't say the general answer.
Well, but in general, if you have a differential algebraic equation, there's no unicity of the solution unless you know something more.
Well, the initial conditions.
No, it's not even enough. If you have, so I'll say algebraic, not ordinary. So
Yeah.
so if you have p of say y prime equals 0, and you just know that say y of 0 is 0,
Mhm.
there's not
Of course.
there's no unicity of the solution. You could add maybe.
No, that's not true.
Maybe if I add more at least, but there's no unicity because at some point it could be that, for example, in the equation there's something like y times y prime,
Mhm.
but if y cancels,
Yes.
then suddenly the equation doesn't have unique solution for y prime. So the derivative is not
Right,
defined.
but you can exclude those initial conditions. So you're saying that arbitrary initial
But-
condition can give you,
Yeah, but then if this thing happens periodically, then you would have to have infinitely many conditions. I don't know if is that clear? Like imagine you had. Let's try to give an example.
no, you
Imagine-
can't do that. If it's polynomial, you can't do that.
Imagine y was something like that. It oscillates.
Yeah.
Every time it cancels, this term would say, okay, now there's no constraint on y prime.
No, your theory was built on already transforming all these sine curves and all that into polynomial equations, right? So when you look at the initials in your polynomial system, it will not have oscillating zeros. It will not have infinite element zero because it's polynomial. The separate is polynomial.
So the things I built, they're not of this form, which is why they don't have this behavior. But if you look at functions like Rubel built them, which are of this form, then they can have this behavior.
No, they're polynomial. See,
It's-
if you take your result and translate back
yes,
to the
but-
analytic sine and cosine and all that, now that's different. But your result is only on polynomial systems.
yes.
In other words,
He is talking about polynomial systems.
right, exactly. It's just like in my paper.
Oh.
But I mean,
But look,
there are two kinds of systems,
my
right?
paper doesn't do this, of course. But I'm trying to tell you that given any polynomial system, the way that you have, you can figure out the domains where you can have unique solutions.
Yes, but we want existence
But
over
you
all
want
of R.
existence for all initial conditions? No.
No, not
No, of
necessarily.
course not, because you fix the alphas.
Yeah,
You choose the alphas.
but I still want to have sufficiently many alphas to approximate any possible f. And for this, Rubel's solution needs so many alphas that you cannot have unicity of the solutions. I just don't know how to explain.
I got lost. What's the question?
I mean, sure, for an equation like this, you could say what is the set of points for which the solution is unique,
Right,
but maybe this set is empty,
okay.
in which case your equation cannot prove a theorem like
Well,
this.
that just simply says that equation is not the right equation.
Yeah, and that's the problem.
Okay.
If Ribel's equation doesn't work, I mean, it works, it proves the theorem, but you don't have unicity. But in general, if you manage to produce an equation of this form, then the unicity is not given. You have to prove it, and usually it's the problem. People don't manage to prove unicity.
But you can compute this. If you're given any system, you can compute the domain of initial conditions where there is guaranteed existence uniqueness.
But maybe it's not enough to approximate ODF.
No, but if you say that, if you give me your polynomial system, that you prove that it can approximate all that,
Yeah?
then you can plug it into my program, at least in principle, to tell you what are the possible alphas.
But
That would, no,
but
that
minus unicity all the time.
that would give you unicity. Not unicity to the approximation of f. Right? Not
No,
that.
you still have the solution.
Yeah,
William,
well, I mean, you're looking for a solution y1, right?
William, are you advertising your program or you
No.
are asking him a question?
Because he didn't.
All right, you don't
follow.
want me to ask? All right, stop. Fine.
Could you, I'm
Fine,
asking you a
talk
question,
about-
William.
no.
Are you asking him a question or?
I
you
am
something?
asking questions.
Could you
I
repeat
don't
the question?
the question.
We lost what the question was.
Okay, all right, then I'll discuss with him, all right? You don't have to listen.
Well, we would like first to understand the question, what the question is. It's a seminar discussion. We all would like to
Well,
understand.
question sometimes doesn't have to be you know, that's what questions are we're discussing, all right? You don't want to
Could you
discuss
ask your
stuff.
question?
I'm trying to understand the result, that's all. Okay. I'll stop.
Or we can discuss it
Thank you.
I'll stop.
offline.